one more concept left, is the sensitivity analysis. The biologists, when they study about population model, what they concern the most is the essential growth rate. And is that a word we call it lambda. You might remember when we talk about the Leslie matrix, that's a very positive result. We got the population growth about 2% per year. That's a very good result. Means they're stable, they're safe, they're not going to be extinct. And when we look at the lionfish model in the previous example, we remember this lambda equals about 113%. That's a big growth. We might be a little bit of control, and that's too fast if you look at this number. So you might give a policy, you say you can harvest, but which one you harvest, how much you harvest, that's a very, very important question. If you look at the lionfish model, only the adult give birth. If you harvest just a few of those adult lionfish, you could suddenly make this whole population extinct. So be careful. So how do we know how much we can, how much is too much? That research is called the sensitivity analysis. Well, it's not a difficult concept when you learn the calculus. It's about the derivative. Think about the change ratio. So make an assumption. In all your model, you got all those transitions. Like this. That's our previous model. And this is the survival rate of the juvenile, and this is the survival rate of the adult. If I harvest, let's say 10% of the adult, and then you're going to reduce this survival rate here by 10%, then your whole matrix changed, and then so is your lambda changed. Then you are going to get the so-called new lambda. And then the ratio between the new growth rate minus the old growth rate over whatever parameter you're looking for the transition parameter, the old one, the new one subtract the old one, this ratio is approximately the partial derivative. Or you just think about the derivative. Now, if I put the pi, the I could be 1 or 2, doesn't matter which one you want to consider. Let's say this is p1, then the I equal 1. Then you can say, let me take 10% of a juvenile as food, fish, as a consumption. And then your pi new will be 90% of the pi old, the old pi. Based on this, the old one is 0.777, if I remember right. And then your new one will be 0.9 times 0.777, probably 0.666, I guess. So that's the denominator. But you need to do a whole new calculation to get this, what I used to call it the eigenvalue, if you remember that. Or you can do another way to look at the ratio after many generations. So if you divide these two, what the sensitivity tell you? If the sensitivity equal 2, another sensitivity equal 20, what's the difference? Whoa, that's a big difference. That means if the sensitivity is 20, you better not to touch that parameter. If you touch, you might destroy the whole population quickly. But if it's 2, you might say, let's harvest a little bit, that's fine. That's the significant. So once you understand this meaning, And the computation is relatively simple. We are going to back into the Leslie matrix. Leslie matrix. And you remember the P1 used to be pointer 15 from the H1. That's the P1. And the P2 used to be, I forget. Let's just change the P1. P2 is let me put a random number. So used to be 15. If I want to increase that transition, and then you add 10% of this 15, you got a 0.165. And then you rewrite the matrix, change the 0.15 into 0.165, and then you are going to get a new number, which is 1.65. You're going to get a 6.5% increase of the population in each year. The old one, if you remember, is 1.216. Well, then the ratio will be 1.062525 minus the old one. Let me write a little bit better. It's 1 point, it's right here, the difference. It's 0.4%. And then you can see that the difference is 10%, is 0.0115, and you find that the sensitivity is about 3. And about 3 means if you make a 10% of a change of that transition, that means the juvenile died because of pollution or anything you like to say, you're going to, this is increase. You're going to have a population increase rate increased by 3 times. But that's not too bad. The danger is when you make the 10% decrease, what's going on? And you can do the same calculation, and then you calculate your new number. And to do the calculation, we found that the sensitivity is 3.0677. That's usually in a normal range. So the analysis indication, if you change this population P1, we're going to make 3 times of impact of the population growth. It depends. The sense is how significant. Only the biologist can interpret that. So let's do to all the 2 different parameters. We got the P1 on the top, and we find that the sensitivity is around 3-ish. Doesn't matter, increase the transition, you increase the growth rate. Decrease the transition, you decrease the growth rate. That's obvious. But you look at the second parameter, oh, you find the sensitivity is much smaller. Well, the sensitivity is only 0.24, regardless it's increase or decrease by 10% or 20%. Well, that just indicates if you harvest some some adult birds died, that will not impact the population as much as the first-year-old. Now, let me back to the 3 ages. This is the transition of P2, and this is the P1. you can see the P1 is almost more than 10 times more sensitive than the P2. We try to explain why, if the survival rate lower in this third age is much less significant than the second age. Well, you look at the birth rate. This lay 10x, this lay 8x. You might remember that. That could be an intuitive explanation. But if you look at the lionfish model of the Lufvicage model, that will be a very different story. If you harvest in the last stage, you can wipe out the population very quickly. The obvious reason is because the whole birth rate given are by the adult. So that's what the sensitivity gives to you. I think the calculation, we can just do the exercise ourselves. Have trouble, I can be the on-call doctor. So all we need to know is the sensitivity. We look at the ratio of the two changes, the parameter change on the denominator and also the growth change on the numerator. And if you do not know partial derivative, that's fine. But if you understand that that's the same concept, except we did not take a limit. Instead, take a limit, we let it go 10%, 5%, 1%, make it small. That's what the limit means. So I finished this hour, and we also conclude the first application, population model. The next one, we are going to look more in the geometric model and use the matrix to express the geometric transition, like a rotation, mirror reflection, shrinking, all those operations. So I will see you next time. Thanks.